Welcome to CS3510. Which one is this? L05A, thank you. And the topic of today is BFS and Dijkstra's. So before we talk about what those are, let's talk about what the context is. We've recently talked about graph algorithms, we talked about DFS, we talked about how DFS can solve kind of a lot of problems. What do we do? Topological sort, directed acyclic graphs. You can use DFS to do cycle detection. You can use DFS to find strongly connected components. A lot of things can be done with DFS. But there are some things immediately we observe DFS can't do, which is solve the single source shortest path problem. So the single source shortest path problem is a problem in graphs, which is you're given a graph, perhaps weighted, perhaps directed, and you're asked to find the shortest distance from some specified known start to all other vertices. So it's not the case, in contrast to other things, for example, all pairs shortest path, which is for every possible pair of vertices, compute the shortest distance between every possible pair. Or given a specific start and a specific end, find exactly and only that distance. That can be solved with a single source shortest path because you compute just that instance it's a subproblem, right? So the single source shortest path is given a start. You know what your start is, but you don't know what your end is. Find the shortest distance from you to everyone else in the graph. And the distance is defined in a directed and weighted sense as the sum of the edges that get you there, right? In a literal Google Maps sense, it's how many miles is each road. If we're considering the unweighted case, we could consider just the number of edges. So suppose we have a graph like this. Just suppose we're in an unweighted sense, and the shortest path then is the number of edges. Right? So we have a graph. What's the shortest path from A to D?
A to D.
Yeah, it's got length 1. But let's suppose we ran DFS on this. What would DFS do? DFS would be at A, it would then go to B, and it would then go to C, and then it would go to D. And DFS would tell you that the shortest path was length 3. But this isn't correct. Obviously, we see the shortest path is length 1. So DFS is really good about going really deep really quickly, and in some sense the difference between DFS and BFS is you should both think of them as primitives for loops over a kind of graph, right? And you can loop over an array, that's pretty easy. How do you quote unquote loop over a graph? All DFS and BFS are is just two ways to loop over the graph, and they're different ways. DFS cannot tell you the shortest distance, but BFS can, right? DFS, you should think of it like this. You go down, and then you go up, and then you go back down, and then you go up, and then you go down, whatever, right? BFS, you should think of as, and everyone know what the B stand for? Breadth, right? So you kind of go like this, and then you discover things that are close to you, and then you discover things that are close to that, and then so on, right? And in that kind of pattern, right? Breadth first search, right? Compared to depth first search. I have to mention that because for like 2.5 years, I thought it was breadth first search, but it's breadth first search. As you have a broad, knowledge. Right. So obviously, we're not going to be able to just take DFS off the shelf, throw that in there, and it's going to solve the problem for us. We need to come at the problem from sort of a different angle, and we want to visit, given a node, we want to visit nodes that are near that node first. By the way, here's another reason that we love the adjacency list data structure, is that we're not randomly looking at edges. If we're looking at A, if we're at some vertex, let's say A, locally, we want to look at the edges that are connected from A. So that one and that one. And in the adjacency list representation, we're just going to loop over those two edges because they're going to be in that list, right? So those are the edges we're going to look at next. If we were trying to compute the shortest path from A to everything, this would have distance of 0. This would have distance of 1, this would have distance of 1, and this would have distance of 2, right? So we need some way that visits the vertices in an order that we would like, in a generic sense, that goes from A and then B to D, or maybe D to B, doesn't matter, and then to C, right? So the way we're going to implement this is with the data structures. Anyone remember the data structure that's used primarily in BFS? Yes?
A queue.
Exactly, it's a queue. So here is the implementation of BFS. You have some graph G, and you have some denoted started vertex, let's say S. What we're going to do is for each V in V, we're going to say dist V takes on infinity. Now, it could be, you know, some implementation-wise, you can't have infinite on the computer. It's some max int value, it's some -1, it's something special that tells you we haven't seen it yet. If we haven't seen it yet, we just say the distance is infinity, right? Many specific ways to implement this, but this is just sort of the generic syntax, right? We're also then going to specify that the start vertex has a distance of 0, right? And again, we're computing we're trying to solve the problem in an unweighted and perhaps even undirected sense. It doesn't really matter here, directedness or not. But here, let's just assume, for simplicity, undirected and unweighted. So the shortest path we're trying to compute is the number of edges, the minimum number of edges, right? So all we're going to do then is begin with a queue of initially only S inside of it. And then as we pop from the queue, we will push children of that node back into the queue. And the way we represent a queue on the board is like this. Things go in the queue in the back of the line, and they exit from the queue in the front, right? So S is going to be in the queue. And then we continue while the queue is not empty. U is going to eject from the front of the queue. And then for each of its outgoing edges, if we have not seen that vertice yet, and then we update its distance. Okay. So here's how the computation works. We have a queue, we pop things off the queue, and we look at all the neighbors of the thing that we just popped off the queue, and we push them in the back of the line. We push those things to the children at the end of the queue, right? There's one small problem that such a thing that you may notice occurs for such an algorithm. There's some subcase that it doesn't really touch really well. Yes?
Disconnected graph.
Yeah, so like if, let's say you have some vertex that's unreachable from S. It's never going to have a distance assigned to it. Its distance will ever stay as like infinity. The way we get around this is we just say we don't care. Like in the shortest path, in the single source shortest path setting, and this is true as we'll cover Dijkstra's and other shortest path algorithms, we assume the graph is connected in the sense that there is a path to every vertex and that it can be reachable. Because if it's not, then you just handle that with a bunch of if statements, and then that's like 1301 and not 3510, right? You can do that some other way. We do the hard stuff, so you guys can do the easy stuff, right? Something like this. So it's in the assumption of every such algorithm is the fact that the graph is connected, right? Especially in this undirected sense, right? Questions on the code before we run through an example and then talk about like why does this work? How do we know this works? By the way, the BFS uses a queue. DFS did not appear to use explicitly a data structure, but I claim it did. What was that data structure? Yes.
Call stack.
Yes, it used the call stack. DFS uses a stack, and we were cheeky about programming it in such a way that it really used the call stack. We kind of abuse, and this is kind of, if you want to implement something fast, but maybe not have the fastest implementation, this is good strategy, is use the call stack as a stack. Every recursive algorithm we did really was stack-based in some sense. But there's no real reason you need to use the literal call stack frame as the stack. It's just convenient and it's a concise representation of the thing. But you could re-implement DFS in a similar way here, where you explicitly say, this is my stack, and then I'm putting things on the stack, and then I'm pulling things off the stack. You could do that explicitly with DFS if you wanted to, but it's just simpler to say, oh, look, recursively, and then this is the stack frame, and it's handled, and everything's nice, right? So really the difference between BFS and DFS is BFS uses a queue and DFS uses a stack. They have the same yin and yang, BFS and DFS, as the stack and the queue do, right? The difference between the stack and the queue is that the last thing to be put in the stack is the first thing to come out. But that's not true in the queue, right? Things come out in order, as they should be, right? Let's run questions on that before we run through a quick example, and we can talk more intimately about like why this works. Yeah. So let's give an example graph. Right. So let's suppose we have the following graph, right? And again, ties are broken alphabetically and so on. And let's just assume we're going to start to compute the single source shortest path from A, right? So what we're going to do is update each vertex's distance value to be 0. A is going to be 0, but each other vertex is going to have its distance value set to be this infinity. Right. The queue will begin with simply A in the stack. It's initialized with just A. Now what we're going to do is pop A off the stack, push everything that's connected to A into the stack, and then update those distances. So when A is removed from the stack, and again it's ejected, we push in its children into the stack. So what are we going to get? BF, right? And also double check me if I make a mistake here. So then we're going to come over here. F is going to have its distance 1 away from a node of distance 0. So it's going to just be distance 1. Right. Now we're going to pop B off the queue and append its children. So F moves forward in line, and then E is added to the end of the line. Right. E is going to have its distance updated to be the distance of the thing it's coming from plus 1. Right. So that's going to be 2. Now we pop F off the stack, off the queue. We eject it, and F is going to, we're going to push its children, which are going to be C, G. So E is going to be in line here, and then we have C and G, right? We're going to update these distances to be 2, 2. And then we're going to, E is going to come off the stack, the queue. So what's going to happen with E? Nothing. But we need to make sure that it goes through the queue before we look at anything else. C is going to come off the queue, and we're going to push its children. Specifically, its unvisited children. The only one of such is D. So G is going to be in line, and then so will D. And then G has a single unvisited child, which, D is supposed to be 3. G has a single unvisited child, which is H. So H is going to have distance 3. Now, D has nothing unvisited, so it's removed from the queue. And then H has nothing unvisited, so it's removed from the queue. Right. Notice that even though there does exist longer paths to, say, H, for example, you could go 1, 2, 3, 4. The shorter path by properties of the queue was found first of 1, 2, 3. So G was able to hit H before D was able to hit H. And that relies on a very important property of the queue, right? So consider you have something like, before we do that, any mistakes, any questions on this example? Right, we kind of are familiar, it's coming back to us about, right? If we have something that looks like this, right? What's going to happen is S is going to be added to the queue. Then A, B, C are going to be added to the queue. And then D is going to be added to the queue, right? It's going to be B, C, D, right? So the property here that's really important, and the reason that the queue works especially well for BFS is the fact that no grandparent and child in queue at the same time. Right? All the children have to be visited. Wait, did I get that right? Maybe I'll word it this way. All children, can I spell that? Children are visited before grandchildren. Right? A, B, and C have to go through the computation. They have to go in line through the queue before D is going to be hit, right? Only the first grandchild is going to be popped out of the queue only after everything before it comes, and those are going to happen to be all the children. So the grandchildren is only going to be looked at after all the children are looked at. That's where we get this nice BFS wave property, right? The exploration happens in a breadth way and not in a depth way. That's the first thing to notice in the computation, right? So even if there are longer paths, by this simple property, we'll find the shorter ones first, okay? First thing to observe is the correctness. Questions on the correctness, right? Are we convinced that it works? Yes. What's the runtime? Everyone remembers it's O of V plus E, but do we remember why?
Each vertex once and go through each edge.
Exactly. We go through each vertex once, and then we go through each edge. Each vertex is going to go through the queue exactly once and not twice. If a vertex has been visited before, we don't look at it again. So each vertex will go through the queue exactly once. Then we look at each edge. Another thing I want to point out is the advantage we have, again, of the adjacency list. We loop over the list. This UV is that list that goes like this, right? Whatever, right? So this for loop is going to loop over the outgoing edges of a specific vertex U. That doesn't mean we have to do random reads or whatever. It's just literally that specific array list of the adjacency list representation. So another benefit of the adjacency list representation of the graph, right? Okay, so that's BFS. Questions on that? So there's always like a heuristic that I'm curious to see what people have learned in like the internet and stuff about when you choose BFS. First off, BFS and DFS, same runtime, identical. V plus C, V plus C. Asymptotically, no difference. Choose one or the other. They're almost interchangeable. But when would you want to choose one over the other? Have you guys been told a heuristic or something like this? Space? Space complexity? How so?
Isn't BFS exhaustive? So you have to. Oh, actually, wait.
I'm curious. Space complexity is such a difficult topic that I spend like one lecture on it in 4510. It's very, very difficult. And most of the time, the best answer to say is don't care about space complexity at all. That's the best heuristic I could tell you at an advanced level. I think at the lower level, space complexity could be dependent upon like, are you sorting, for example, in memory, or are you making copies of things, and is that expensive? And those kinds of factors end up getting evaporated by the big O anyway. So I could see something in a very serious, practical way be a difference between these two, but maybe not in the big O, right? But when would you choose BFS over DFS? Yeah.
Well, for DFS over BFS, you would do it when you have like a goal state, or like a goal.
Okay.
It's like when you have a goal, you want to go DFS because you might you're going to hit like a leaf state first.
I see. Okay. Yeah.
DFS ensures an optimal solution because DFS can like go down an infinite path.
I see. If you have some sort of infinite graph, that sometimes you do have an infinite graph, and you could choose BFS over DFS. I think these are good answers. What I was told, and it doesn't really matter, is that you want to choose BFS when the solution is close to you, right? In the sense of it's not too far away from your target. Now, again, big O, this doesn't matter at all. But if the solution is close to you, then you would probably want to do BFS. For example, if you're exploring, for example, the game tree of chess, you don't want to use DFS because you could go down some very infinitely long path of a sequence of moves. But you might miss a checkmate in 3 or something like this, right? So you would want to choose BFS over DFS in that sense. Now, if it doesn't matter, if there's some bounded depth and your graph is pretty stubby or something, you probably DFS would work fine. This heuristic is not as important, and I think maybe you have been told something similar to this. It's not as important as the fact that DFS has many applications that don't sound like they use DFS. Cycle detection, topological sort, and strongly connected components. But the one thing you would want BFS over DFS is if your problem is phrased in a way as a shortest path problem. Right? That's really the big difference between the two. And it's not often the case that they are interchangeable. BFS explicitly solves this unweighted shortest path problem in a way that DFS could never. And that's really the best way to take BFS over DFS. Right? I can tell you one more practical problem that comes up quite often when you would want to choose BFS over anything else. And my favorite graph problems are the kind that the problem is not given to you in such a way that you would ever use, it doesn't sound like it needs a graph. And the problem specifically is like, suppose you're given a chessboard, right? Sorry, let me change that. Suppose you're given a chessboard, n by n, 8 by 8, doesn't matter. And you're given a specific square on that chessboard. And you want to find, and you're also given a knight. Everyone know what the knight does? Anyone not play chess and not know what the knight, right? The horsey, L shape, right? So it's allowed to jump in like L-shaped squares, right? So you're given a chessboard, you're given a position of the square on the chessboard. And you want to determine the minimum number of moves that would take the knight in terms of its hops to reach that specific square. So the coordinates of the square are part of your input. And let's say the board is 8 by 8, something like this. How can you efficiently solve such a problem? And the answer, it doesn't sound like this, but this is actually a graph problem. This is actually BFS. What you do is you don't need to necessarily construct the graph, but you would make a graph and all of its, for example, let's say it's like this, right? You would make this an edge, quote unquote, anything that was reachable from the knight at that specific state. Right? The trick to note, and you don't need to necessarily construct the graph, but you need to know, oh, it's BFS, and therefore I would use the Q, right, over a stack or something like this. This can really only be solved with something like BFS, and it's not necessarily true that it's a BFS even over a specific graph, but it is BFS. The key word to know that you would need BFS for a problem like this is minimum. It says the minimum distance, right? You don't want to find any distance or the number of times you can hit the square or anything complicated like that. You don't even want to determine if a square is reachable at all. You want the minimum distance, the minimum number of moves you can make to reach such a square. And BFS will find this before other things will, right? Questions on that? Have you guys seen the night hop problem in some? I think this is a fairly popular problem. So, all right. Any more questions on BFS? All right. Now the next question you should have is on DFS. Dijkstra's, basically. We did it in the unweighted shortest path. Unweighted shortest path, where the shortest path is defined as the sum of the number of edges, right? But if you're working in a weighted graph where the edges are not just weight 1, how could you solve this problem, right? So a weighted graph might look something like this. Right? So in a weighted graph, the shortest distance may not be the number of edges because you would consider the sum of the distances on that path towards that edge. So for example, for here, there's an edge of length 1. There's one edge, but it's got a weight of 100. So there's a shorter path, quote unquote, that takes more edges, something like this. So BFS won't solve this problem immediately and directly, right? If I were to give you a specific example, you could do something like, this is a classic example. Suppose you have something like this, A, B, C, let's say. Right? And let's suppose we wanted to compute the shortest path for all these vertices. What's the shortest path from A to C?
150.
Yeah, it's 150. You go it's small enough you can just do it in your head. You go A to B, you go, okay, that's 100, and then I go B to C, that's 50. So 100 plus 50 is 150, right? And that's less than 200, so the shortest path, that's the only other path. So it's 150. First problem is, how do you know that's the only path? So in a graph, you kind of have to make sure that some property emerges that you are guaranteed that your shortest path is also the only path, and you haven't missed some shorter path, something like this, right? Also, by the way, there's a fun fact about this specific graph. There's a problem with it. Not really a problem, but does anyone notice anything strange about this graph? You could never get to A? Well, let's suppose you start from A. So you single source, let's just always assume that it's nice that you're already there, right? That's not the real problem, actually, but there is no cycle? There's a cycle. This is not very important. It's just it's a kind of a fun fact, trivia. This graph is strange. Suppose the edge weights are distances in the sense of Google Maps, literal miles. Yeah.
This is the graph of I-85 in downtown Atlanta. We're going through the interstate is way slower than going around through like.
You know, when there is traffic, yeah, it tells you to take 285 instead of the quote-unquote shorter path of 85. We'll talk about traffic planning in the context of network flows at the end of the semester. So we can actually solve such a problem, and you could basically prove the Atlanta designers don't really do a good job on purpose for the traffic pattern. But that's not exactly the answer I'm looking for. Have you guys heard of the triangle inequality? No, Jim? Basically, this is not you can never, if the earth is flat, you can never build such a sequence of roads, right? The triangle inequality says the sum of any two sides must be greater than the third. You could never have a triangle of side length 200 here, and then a side length of 100, and then a side length of 50, because the distance between those, in a Euclidean geometry sense, would have to exceed. The triangle inequality says the sum of any two sides must be greater than the third. So the only way to actually build such a sequence of roads that would have such a problem like this is if like one wrapped around the equator or something weird, right? In a sphere or something weird. But that's not important necessarily, and we're not working in a geometric sense. A graph is independent of how it's arranged onto the plane. And sometimes you can get speedups if you assume the graph is Euclidean, if it obeys a triangle inequality. You can make faster algorithms. But in some sense, the graph not for us. The graph doesn't matter how you position it, it's just what it is, right? Here's a hack you could do to get BFS without any modifications to work on a weighted directed graph. Replace every weighted node by a sequence of nodes. Okay, so here I've put 99 nodes and 100 edges. It's unweighted. Here I've put 199 nodes and 200 edges, 49 vertices. So I've increased the number of vertices. Forget the time it takes to compute such a graph. But let's first observe that BFS, when you run on such a graph, will be correct, right? Basically, the motivation, the point we're doing this is that all Dijkstra's is, and you guys have seen Dijkstra's, I'm sure, in some previous class, right? 1332, maybe. All Dijkstra's is just a generalization of BFS that works on weighted graphs. So it's like almost the same algorithm. So if you take the same spirit of it, it's going to like work the same, right? This is the graph that's going to work. Now let's run BFS on this graph, starting from A. What's going to happen is we're going to reach those two vertices, and then we're going to reach those two vertices, and then we're going to reach those two vertices, and so on, right? So those are going to be the things in the queue. We're going to pop one, push the pop one, push pop, right? We're going to go down these two paths. Now this has 100 vertices, and this has 200. So what's going to happen is we're going to be, let's say we hit 150 vertices. We're going to be 150 edges, excuse me. We're going to be around here on one part of the BFS, and the other part of the BFS is only going to be about 150 of 200, so like 3/4 of it. So it's going to be like right there, right? So BFS is going to go quicker through here because there's less edges than it's going to go through here. This is approximately, let's say, 150 edges, right? So it'll reach C from here and mark it before it goes through here and marks it, right? So this technically works. This does find the shortest path. This is a way to convert the shortest path to a problem that BFS can just solve off the shelf. two problems. One, doesn't work with negative edges. You can't have negative number of vertices. Don't ask me about negative edges yet. We're going to have an entire lecture. There's so much complicated stuff that occurs when you add negative edge weights. It's not as simple as you think. It's a very, very, even today there are people coming up with new algorithms. There was an article about it like a year or two ago that people found an even faster algorithm. Dijkstra is basically so elegant, it solves it basically optimally. It's a beautiful algorithm. But the negative edge weights are so ugly that people are still working. This is active research. People are in the mines right now trying to figure this stuff out. So we'll have a whole lecture on why that's difficult. So hold your patience on that one. We'll come back to that. So first off, it doesn't work with negatives, though. It can't have negative vertices. Number two, what's another reason this is bad? Yeah, I mean, yeah, whatever you guys said. It's a lot of everything, right? You have, like, let's say you have to write down the graph. That would take a lot of space. How much time would this take? Give me an upper bound, like a loose upper bound.
Convert all the edges that way.
Yeah, it's a function not of the number of nodes of the graph, but of the max weight of an edge in the graph, right? So if you had, for example, something like that, it would take that many steps, right? Now, although the graph would be represented in the weighted sense in a much more concise way, because it takes log number of bits to represent a number n, right? But it would take a function of n and not a function of log of n. So in some sense, this is like exponentially bad, right? So how can we fix it? This is not like, besides the time, this is not such a terrible idea. Because what this really does, it also tells us to reach B before reaching C by sort of pacing ourselves through there, right? In some sense, these weird edges with several vertices on them act kind of like timers for us, where this one slows us down, and we know to hit this one before this one. So it's as if we were comparing, so for example, when you want to compare, let's say 7 and 6, you want to say, is 7 greater than 6? Well, then you first ask, is 6 greater than 5? And then you say, well, okay, well, is 5 greater than 4? Is 4 greater than 3? Is 1 greater than 0? Yes. And then that's the way the computation in this weird way works. Why do that? You don't need to do any of that. Just say, is 7 greater than 6? And then just be like, yeah. So what that means is you go to the shorter path. You would choose to go to B, which has 100, over C, which has 200. So just directly compare 100 and 200, and then choose B over C. That's all it is. That's all Dijkstra's is there's a little bit more around it, but that's basically all it is. Is this, instead of choosing nodes as they come out of the queue, you choose nodes that currently have the shortest distance set for them. And as those come out of the queue, the rest of the graph has this nice property that everything works out beautifully. Okay. Question on this analogy before we get to the code? Okay. Anyone remember the data structure that Dijkstra's is built upon? Yes.
Priority queue.
Priority queue. That's crazy, isn't it? BFS is built on a queue, and then Dijkstra's is built on a priority queue, and those sound like the same thing. So it turns out, yeah, the same way that Dijkstra's is a generalization of BFS, which uses a queue, the generalization of BFS is going to just use the priority queue. And we're going to have, after the break, a whole little spiel on priority queue implementations and like certain things like this. Dijkstra's is a very elegant algorithm, but the only downside of it in terms of communication is that it's highly data structure dependent on which way you choose to implement the priority queue. So we'll talk about the analysis and the runtime later, because that actually does matter. Unlike BFS or DFS, which are largely independent of those, it does matter for Dijkstra's. So a priority queue, everyone remember what a priority queue does? Vaguely? Let's just talk about its basic operations. So the priority queue implementation, in a black box way, has the following operations. It has the ability of insertion. We can decrease a key in the sense that there are items here that are keyed by certain values. And given an item, we can say, hey, decrease the value of that item. Decrease its key. And it'll have a higher priority, right? Then we can say, delete min. And then make queue. So given a set of uninstantiated objects, you could make the queue from those. We'll talk specifically about this. By the way, what data structure is used to make a priority queue? Binary tree, yeah. This is a binary, it's a binary heap, right? Use the heap. So we're going to talk about heaps after the break. The other way you could do it is with not much worse runtime, it turns out, with just an array. You could implement all these objects on the array, right? For example, to delete min, you just loop over the array, find the minimum element, and then delete it. Making queue is just filling the array, and so on, right? So let's talk about how Dijkstra's work. And how is the information encoded in the graph, right? So the graph is a set of vertices and directed edges with weights on them. So you could have the adjacency list representation have the weights stored in there. Or you can kind of just keep it as like a dictionary, which is what we'll do. We'll keep it in this external data structure called L, which is just going to store the weights for us. And these are assumed to be non-negative, right? No negatives allowed, and S is going to be our start. For each u in v, we said dist u equals infinity. Prev of u is equal to null. Here's something nobody asked me about. Our implementation of BFS does not return what the actual shortest path is. It just returns the length of the shortest path. And especially in this class, those kinds of things are easy to conflate because it doesn't really matter. If you have the ability to compute a numerical answer, for example, the minimum element or something like this, you can also almost always, with just a little bit of bookkeeping, keep track of, for example, where the minimum element is. So this version of BFS keeps track for us what the shortest paths are, because this dist will contain integers. It'll contain numbers, 0, 1, 2, 3, and so on. But it doesn't tell you, for example, it'll tell you, for example, the shortest path to D is length 3, but it won't tell you what that actual shortest path is. So we just do a little bit of bookkeeping to make sure that we also have not just the length of the shortest path, because we don't want to know, like, okay, from here to there it's 27 miles, but we want to know the actual route. That's basically what we're going to do in a little bit of bookkeeping. The way we do so is with what's called a prev array. And all this does is a bunch of pointers to where you're coming from. So for example, if the shortest distance to you goes through some vertex v, then we would set prev of u to be v. And then we would recursively say, okay, what's prev of v, and so on. And using those back pointers, we could get all the way back to the start. And so that's going to keep track of the actual path for us, while dist keeps track of the actual unit, the sum of the edges, the distance itself, right? Not too hard to say. It's interchangeable, right? In the future, if we don't keep track of, for example, the actual path and just keep track of the numerical answer of the path, things like this always work. It's an implementation detail more than anything to solve the problem, right? The start vertex is going to be 0. We're going to make the queue. And these are going to be keyed by the distance values. And observe at the beginning the distance values. How do you make a queue? In any implementation of a queue. You guys know heap sort, right? Remember something about this? Question? Oh, okay. Yeah.
You can use like an array and then what form of a queue would that?
Yeah, suppose we have our queue implemented as an array. So the make queue operation, the distances of all objects are going to be 0 and then infinity. So it's going to have a 0 and then it's going to be infinity, 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 right? So in the array simple, it's pretty simple, right? When you make a queue in for other data structures, you can do insertions. But because we're working in a specific case that all the elements except one have equal value, you can actually do it faster than inserting something v times, right? Again, we'll have to talk about that. While the queue is not empty, we're going to pick the minimum element off of it by deleting the min. And then for each of its outgoing edges, if there is a shorter path through U, if the current distance to V exceeds the distance of U plus the length of LUV, then update that. Set the back pointer of prev of V, and then we're going to decrease key of in the Q of V to dist V. All right, that's it. That's all Dijkstra's is. But why does it work? Right? This coming back to you. We've all seen Dijkstra's. This is starting to ring some bells. Why does it work? There's really two simple properties for the reason Dijkstra's work. And by the way, again, Dijkstra's only works on positive edge weights. So there's two real good reasons it works. First off, every efficient algorithm exploits something about the problem structure. It doesn't matter what it is, right? But there's every problem has a really stupid brute force solution. Every problem that you care about can be brute forced. So if you have an efficient algorithm for something, it means that you understand the problem at a deeper level than someone who understands nothing, right? Every efficient algorithm has to exploit some structure of the problem. And the first structure that we have about graphs is the fact that paths in graphs are extremely local, right? If I were to word this in English, the property that's exploited is something like the shortest ST path is less than or equal than the shortest SUT path for all U. So first off, kind of think about that for a second. Pretty trivial. The shortest path from S to T is the shortest path from S to T through U for every possible U, right? That's kind of what really happens here. When you think about this update, the way to think about it is that we are at some start S, and we go to some, let's say, V here, and there's some pre-aligned amount that's already been computed from some other paths, right, which is dist V currently, right? But then you have a shortest path to U. U is ejected from the Q, and it's currently at dist U. And you know that dist of U must be less than dist of V. Why? Because you're deleting the min. U is coming out of the Q and not V, right? But it happens to be the case that there's an edge from U to V. So when you have a structure like this in the graph, it's like, when you ask a question like this, it's like, all right, is there a shorter path to V through U, or is the current shortest path shorter? Whichever one you take the min of both of those, and that'll give you the shortest path, right? So the question that's being asked here is there a shorter path through U to V, or just what's already been stored through other things that have been popped off the queue, right? As we update and we compute shortest paths. That's all basic. That's the first property, the reason this works. Questions on that? Do we believe me that these two basically are the same, right? And every graph algorithm that computes shortest path, by the way, is basically going to use something, different ways to program it, but it's basically going to use that property of graphs. Any questions on that kind of analogy first? Now the second thing is, how do we know we've popped U off the queue? How do we know that we found the shortest path to U? We're not going to look at, U is never going back in the queue, right? It's been visited. How do we know, first of all, that U is never going back in the queue? Sure, but how do we know that there's not a shorter path to U that would put it back in the queue? Yes?
I guess the first parent that puts you in the queue must be the shortest, or the first one to do it, so it's going to be the shortest path.
Yeah, in the other way, I would say all the other ones must be longer. So, for example, let's say you have U, and then you have V, and let's say you have W and something. And let's say the shortest path to U right now is like 15, and let's say the shortest path to V is like 22, and then W is 25, something like this, right? If you eject this, in the priority queue implementation, you eject the minimum, right? So U is going to pop out of the queue. All the other ones that are currently in the queue have larger distances stored from them. So even if there was an edge from V to U, let's say, the current distance to V is 22. So any distance that's going to go from V to U is going to be greater than or equal to 22. Why? There's no negative edges. So we know that the distance, any distance through U, to U, from any of these other weights has to exceed those values. The shortest distance to U from V is going to be greater than 22. Any path that goes through W to U is going to be greater than 25, and so on. Why? Because those are less priority in the queue. U, being at the front of the queue, means that everything else has longer paths currently. So we know that if we pop U out of the queue, we can guarantee ourselves that we've actually found the shortest path to U. Why? Because it's ejected. The fact that it's ejected means we found its shortest path. Everything else has longer paths to it. So that's kind of the correctness about why does Dijkstra's find the shortest path, right? Now again, observe very intimately how that relies on positive edge weights. If there's an edge of negative 22 from V to U, that doesn't hold anymore because the shortest path goes through V, and you have to put U back in the queue or something, right? We'll talk about that later, but like this doesn't hold in negative weights, first of all. This correctness part, this nice property that we're promised to find the shortest path, only works when edge weights are positive, right? Any questions on the correctness before we get into doing an example? Right? So suppose we have the following graph. Okay? So at the beginning, let's just set our Q to be as follows. Right? We update the distances for A to be 0 and all these others to be infinite, right? And let the column represent the Q at a different time step, right? So we eject A first, right? That's the one with the minimum. What updates happen when we eject A? Yeah, B and C are the only things that are outgoing from here. So we update the distance to B to be the distance to A plus this edge weight. Why? Because 0 plus 4 is less than infinity. So this is going to update to 4. 0 plus 2 is 2, which is less than infinity. So this is going to update to 2. Okay. Now, which is the minimal element? Yeah, we're going to eject C now. What updates? C has an outgoing edge to B. And C has current distance 2. So is 2 plus 1 less than 4? So we update this to 3. Notice that the shortest path to B previously was through A. But now that we've found the shortest path to C, we can remove it and say, hey, actually, there's a shorter path to B, not directly, but through C. So this is a shorter path to B than this. And we did so by popping C off the queue, right? What else updates? There's a path to D, which is length 4. The edge is length 4. So what's the shortest distance currently to D? Yes, it's going to be 2 plus 4 is 6. What about E? There's an edge length of 5 from C to E. And we already know the shortest path to C is 2. So we know that 2 plus 5 is 7. So this is going to be 7. We updated those because those are on less than infinity, right? All right, what's the next thing we're going to eject? Yeah, 3 is the minimum here. So what outgoing edges are there for B? Now notice that there is a weight. We look at that there's an outgoing edge from B to C of weight 3, right? B has weight 3, and there is an edge from B to C of weight 3. So there is a path of distance 6 to C, but the shortest path to C is already 2. C, we already know that C is never going back in the queue, but this basically confirms it for us. Like even if you, it doesn't matter or not whether you add an if statement, don't add it back to the queue, it doesn't matter. Because the shortest path for C was already found. So just by the properties, it's never going to have to, the shortest path is never going to go back there, right? Because also the shortest path to C, to B goes through C already. So that path of length 6 is like this. Of course that's going to be longer than the path that just goes straight to C. So we ignore that edge, that outgoing edge. B goes to C, but we don't update it, right? Questions on that? Why we don't update it? Okay. There's an outgoing edge from B to D of 2. The current shortest path to B is 3. 3 plus 2 is 5, and 5 is less than 6. So we would update that. Okay. Then B has an edge of weight 3 from B to E. The shortest path to B currently is 3. 3 plus 3 is 6, which is less than the current shortest path of 7. So this will be 6. And then what happens? What do we eject next? Yeah. Sorry. We eject D. We already ejected C at the beginning. So we're going to eject D. Does anything update? D has no outgoing edges, so no. What about, then we eject E, right? And does D have E has an outgoing edge of weight 1, but it's, the shortest path to E is weight 6. So 6 plus 1 is 7, so that would be a path of length 7 to D. But the shortest path to D is already 5, so we also don't update. So this is the shortest paths in that sense, right? The shortest paths then in order are going to be what? 0, 3, 2, 5, and 6, right? Those are our final answers of the actual distance. But what is the literal shortest path? Well, had we kept track of the back pointers, it would look like the following. The shortest path to B does go through C. And the shortest path to D goes through B. And the shortest path to E goes through D. Yes. So this would be the actual path. And then those would be the distance of the path, right? So if you wanted to figure out how to get through D, you would say, oh, it's A to C to B to D. But these would be stored as the back pointers, right? Prev of D is B, prev of B is C, and prev of C is A, and so on, right? Okay. Questions? Dijkstra's? What's the runtime of Dijkstra's? Let's talk about it after the break.